This is FRQ number 5 from the 2025 AP Calc BC exam. This problem involves a little bit from AB and a little bit from BC. So they tell you y equals f of x is a particular solution to this differential equation that has the initial condition when x is 1, the y value is -1. In part A, they ask us to find the second derivative of f evaluated at 1, so the value of the second derivative at the ordered pair 1, -1. Show the work that leads to your answer. So I'm going to start by taking my second derivative. So I'm taking the derivative of the left side of this equation to generate that second derivative. Now when I take the derivative on the right side of the equation, I am going to be needing to use a product rule. The derivative of 3 minus x is -1 times the original second piece plus the original first piece, and then the derivative of y squared taken implicitly is going to be a special application of the chain rule. Here's the derivative of the outer function with the inner function left inside, and then times the derivative of the inner function to finish that off. Now what I want to do is I want to evaluate the second derivative at 1, -1. So I'm simply putting -1 in place of these y's. I'm putting 1 in place of this x. Now the other thing that I realize I need here is I need the value of the first derivative at this ordered pair in order to complete my calculation. So I've got a little bit of extra work in the upper corner here. If I put +1 in place of this x, -1 in place of this x, the value of the first derivative at this ordered pair is 2. So I'm putting 2 in this position. This right here would receive full credit. If you do simplify, you end up with -9 for the value of that second derivative. Part B asks us to write the second degree Taylor polynomial for f based at x equals 1. So what I went ahead and did is I wrote in general what the second degree polynomial based at 1 is going to look like for any function f. So what I realize I'm going to need is I'm going to need f of 1, f prime of 1, and f double prime of 1 to complete those numerators. And I know that f of 1 is -1. So if I put -1 here, divided by 0 factorial is 1, keep in mind, and then anything to the 0 power is 1, I get -1 for that first term. Does not have to be simplified, but I do need to replace f of 1 with its numerical value. F prime of 1 divided by 1 factorial is just f prime of 1. We computed that back in part A. That was in the upper right corner of the page, right? Evaluate the first derivative at that ordered pair, and we got a value of 2. And then the second derivative evaluated at 1 divided by 2 factorial. 2 factorial is 2, keep in mind. That's going to be our -9, our result from part A, in front of that x minus 1 squared. So there is our second degree Taylor polynomial for this function based at 1. Part C. Second degree polynomial for f about 1 is used to approximate f of 1.1. Given that the third derivative of this function evaluated at any x is always going to be less than or equal to 60 for all x between 1 and 1.1, use the Lagrange error bound to show that this approximation differs from f of 1.1 by at most 1/100th. Okay, so what I did is I started with Taylor's remainder. The exact difference between the function value at 1.1 and the second degree Taylor polynomial value at 1.1 is going to be established by this expression here. The third derivative evaluated at z divided by 3 factorial times 1.1 is where I'm making my estimate. So 1.1 is going in place of where you would normally see an x in that formula, minus where the polynomial is based, raised to the third power. Taylor's remainder says that there's some value z that sits between 1 and 1.1 that makes up this error perfectly. It's difficult to find that exact value of z. The Lagrange error bound is going to require for us to identify the maximum value that this expression can ever be. So I know that that exact error, and I've got absolute values here to denote that I don't care about the direction of the error, I just care about the magnitude of the error. That exact error is guaranteed to be less than the biggest that this numerator can ever be on the interval where z has to lie. The biggest this value can ever be on the interval where z has to lie is 60. So if I simply put a 60 here, I have an upper bound for my error, the Lagrange error bound. So I do have to show that this is at most 0.001, 1/100th. So I do want to try to clean this up a little bit. So 3 factorial is 6. You see I wrote a 6 there. If I cube 1, I stay at a 1. If I cube 10, though, I get to 1,000. So what this ends up being is 60 over 6 times 1,000. That actually reduces to 1/100th, which is equal to that decimal. Our exact error with the second degree polynomial estimate is definitely going to be less than 1/100th. Last part of this asks us to use Euler's method starting at an x value of 1 with 2 steps of equal size to approximate f of 1.4. Show the work that leads to your answer. So I like to structure my work when I use Euler's method in table form here. So I've got my x's here, and then I've got my approximate y values showing up in this next column. Now this is an exact y value, but any of these other y values that I establish are going to be estimates. Now the way that I'm going to find the y value that corresponds, the approximate y value that corresponds to the x of 1.2, so the way that I find my next y is I take my current y and I add on the slope of the tangent line at the currently completed ordered pair times my step size. Now my step size, if I'm getting from 1 to 1.4 with 2 steps of equal size, I'm going up from 1 to 1.2 and then up again from 1.2 to 1.4. So the y value at 1.2 is going to be approximated by taking the current y, -1, plus the value of the derivative at the currently completed ordered pair, 1, -1. And again, that's that value from back in the upper corner from the work in part A, +2, and then times the step size. This ends up being -0.6. So my approximate y value at 1.2 is -0.6. Now my approximate y value at 1.4 is going to be found in a similar way by using this currently completed ordered pair. So I'm going to take the y that I just generated, -0.6, plus the value of the derivative at this ordered pair, 1.2, -0.6. So in the first derivative here, I put 1.2 in place of this x. I put -0.6 in place of the y, and then I'm multiplying by the step size. The reason why I boxed this up, this will receive full credit for part D. Your answer does not have to be simplified. Some of this work that I've done down here is a partial simplification of this answer. It is a mess doing work with fractions, and I didn't even bother finding the common denominator here and trying to go to a specific end result. I left my answer unsimplified here. You waste time, you take on a lot of risk of making some silly arithmetic error. I may even have one showing up here. I just kind of tapped out on this, but full credit for part D established by what's in this box.